Good afternoon. So we are Group 33 with Srimad, Akul and myself Abhishek. Today we are here with the last and final update for our project, a multimodal neural network for skin cancer detection. Skin cancer, especially the type called melanoma, is having a high mortality rate when it is detected late. So early diagnosis can improve the survival rate. However, there is a gap. Access to dermatologists and specialized equipment is limited in many areas. Our goal is to develop an accessible AI tool so that we can easily detect the skin cancer as early as possible. Our data is sourced from ISIC. What did we have? We have images cropped from 3D photos. In the data, we have had 400,000 samples with over 100 columns. We had HDFI images for all these samples, which are efficiently compressed, and we also had individual JPEGs. Our target column was binary, either 0 and 0 or 1. Our goal was to output a probability score between 0 and 1, indicating the likelihood of the malignancy. Our inputs are high-resolution images and its metadata. Metadata included like age, sex, anatomy site, diameter of the lesion, contract, asymmetry, and color variation in the lesion, and many, many more. The final output is the continuous probability that we thresholded for a binary prediction, 0 for likely being benign and 1 for likely being malignant, which were our binary target next to Sriman. Yeah.
So to get started, we performed EDA. So this is a summary of that EDA. We came to know that the dataset is large and it's highly imbalanced. So we have only 0.1% of the data that is actually malignant. So there's a high imbalance. We have a rich metadata with predictive potential. So we have the core features, that is the images, and the total body photography features like the color shape. And the images are stored efficiently as HDFI. So before we go into EDA, let's take a look at the methodology. So we performed imputation of missing data. We encoded our categorical variables. We scaled our numericals to range, and we normalized our images as a standard procedure. Then we went ahead with modeling where we had to address the imbalance. So we used a stratified train validation split. And for evaluation, we used our AUC F1 sensitivity and specificity metrics. So for missing values, you can see that there's a lot of missing values for some classes because these classes are uh, particular to melanoma. So for example, IDXS5 shows us what scale the melanoma is in. So it might be missing for most of the columns since not most are malignant. So we had to impute all of these values. And for things like sex and age and anatomy site, we used mean value to imputation. So this is our EDA. So we performed EDA for different features like delta binom, symmetry across two axes, or area to perimeter ratio. So delta binom tells us whether the color difference between the lesion and the surrounding skin. This two axis symmetry, that should be pretty understandable. And then we have the area to perimeter ratio. And we also have radial color. So in concentric circles along the lesion, you can see how the color changes, which might be an important feature as well. So all of these, we plotted the values, we took the ranges and saw if there's any clear differences, and there were not many, but these are still very important features. So coming to the baseline, we used logistic regression, random forest, MLP, CNN, and Resonate 18. So for the first three, we did not put in the images. We used a statistics-based method where we took the mean and standard deviation of the RGB channels and passed that on to the models. And for CNN and Resonate, it was just the direct images that were passed in. You can see that CNN performed best across most metrics, and logistic regression was not far behind. So there's no clear dominance between image features and tabular features or statistics features. Then we chose on the final architecture to be a CNN and an MLP fusion and CNN plus XGBoost. So CNN is used for the images part and MLP or XGBoost is used for the tabular features, which is the metadata that we're talking about, the texture, the color, the shape, and so on. So we have a Resonate 18 backbone and we bring in the tabular branch and we merge both of those together and we train using a weighted binary cross entropy and Adam optimizer to get our results. Similar for XGBoost, we are using 200 trees to extract the features, and we combine the CNN and the feature vectors together and pass it on to XGBoost. So all of this has been optimized for the extreme imbalance that we are seeing in the dataset. And these are our final results, which will be told by Akul.
Yeah, so coming to the final results, our best performing model was CNN XGBoost, achieving an AUC of 91 and an F1 score of 83, which demonstrates strong performance in detecting malignant lesions. While CNN and MLP had slightly higher recall, it came at the cost of lower precision, making CNN XGBoost the more balanced choice overall. A key takeaway was that Hybrid models combining images with patient metadata consistently outperformed models using only one input type. So this fusion allowed us to capture both visual and contextual signals critical for early skin cancer detection. We tackled the extreme class imbalances using weighted loss and undersampling, since malignant cases were less than 0.1% of the dataset. Interestingly, features like color contrast and hue variation emerged as strong predictors, while spatial metadata from total body photography also showed good importance. In conclusion, hybrid architectures proved most effective, especially under data constraints. Moving forward, we aim to optimize the model further and validate on external data sets to ensure robustness in real world applications. So these are our references, and thank you.